MOSFET. MOSFET, it is a transistor. It is a basic element in the modern electronics or VLSI field. If you see MOSFET, see the abbreviation, it is a transistor. It contains metal oxide semiconductor field effect transistor. The MOSFET full form is metal oxide semiconductor field effect transistor. Before learning MOSFET, we need to know MOSCAP. MOSFET, the basic is we need to know MOSCAP. This is metal oxide, same MOS. Capacitor, cap has to capacitor. MOS is metal oxide semiconductor. So you have 3 layers in MOSCAP, which is you will have a semiconductor and oxide and a metal. Capacitor is, what is capacitor? Capacitor is an insulator sandwiched between two conductors, like this. This is the capacitor. You will have an insulator here. It is sandwiched between these two are conducting plates. Based on the voltage applied on gate, I will tell you what is gate. Applied on gate, here the gate is the metal. The capacitance of MOSCAP varies. So that means the MOSCAP is acting as a variable capacitor. This MOSCAP has 3 regions of operation. They are 1. Accumulation, 2. Depletion, and 3. Inversion. This is the MOSCAP. I have a metal layer and an oxide layer. Let my semiconductor layer is P-type. I hope you know what is P-type semiconductor and what is N-type semiconductor. P-type semiconductor has majority carriers are holes and minority carriers are electrons. For n-type semiconductor, majority carriers are electrons and minority carriers are holes. Now if I apply a voltage, this is we are terming as gate. Why gate? I will come. It's nothing but terminology of a MOSFET, where you have a gate and a drain and a source and drain. It's like a pipe where the flow starts from source and flow ends towards the drain. The control is by a gate. Based on this control, the rate of flow between this source to drain will be controlled. This is the operation of MOSFET. Now if I apply a negative voltage here, on gate, what will happen? This will polarize the oxide layer and what will it make? The layer polarizing means the positive and negative voltages. It will polarizing means it will separate the positive and negative voltages in the oxide layer. That means this negative voltage attracts the positive charges in the oxide layer this side and negative charges in this side. Now this negative charge leads to accumulation of holes. What are the majority carriers in this p-type? It are holes. These majority carriers holes are positive charges and these will be attracted towards this interface of oxide and this semiconductor. That means holes are accumulated at the interface. And this is called accumulation of holes. So now there is a conducting layer metal. This is conducting layer and this is also a conducting layer. Between two there is an insulator. So now what if you see this resembles a parallel plate capacitor. If you write equation for capacitance, if we write equation for capacitance of a parallel plate capacitor, what it is, epsilon A by D. C is epsilon A by D. This is cross section area, this is distance between the parallel plates, and epsilon is the permittivity of the material used in the insulator. So here oxide is the epsilon, oxide is silicon dioxide or any oxide, and area and D. So you have a capacitance now. So for negative voltages, if we draw a curve between the voltage and capacitance, so for negative voltages, what it will be, there is some capacitance C accumulated. So this is CV curve. I will come back to the CV curve and significance of the CV curve. Let's apply now. Let us apply a positive voltage on gate. Now if you apply, let's draw the MOSCAP again, and we are considering only P-type semiconductor. You can consider N-type also, we will see it later. So this is gate, this is metal, this is oxide, and this is P-type semiconductor. Now if I apply a positive voltage, so what will happen? So again the charge in the oxide will polarize. Charge in the oxide gets polarized. Now the negative charges come this side and positive charges come this side. Now what will happen? So P-type semiconductor, the P-type semiconductor has majority holes. So these holes, the holes get repelled or depleted by the positive charge, and we will get a depleted region which consists of only immobile ions. So now there won't be any holes, there will be only immobile ions, there won't be any holes. Holes will be depleted from this region, and this region is called depletion region. So now the entire insulator, this entire thing is insulating region. So this extra area, this extra capacitance is called depletion capacitance. CD. Now if you see the parallel plate capacitor, it looks like the initial capacitance in series with this depletion capacitance. If two capacitances are in series, what will happen? The resultant capacitance is less. You can find like the resultant C is C naught CD per C naught plus CD. So if we draw again the CV curve, So what will happen for negative region? It is some capacitance, and for positive voltages the capacitance reduce up to some minimum capacitance. Now see what will happen after this minimum capacitance. Now if I increase this voltage further, more positive, suppose let me draw the MOSCAP again. You will have metal layer, oxide layer and semiconductor layer. We are assuming it as p-type here. Let be the metal, oxide and the semiconductor. We assume it as p-type. If I apply more positive voltage, more positive voltage here, what will happen? Now the oxide gets polarized, as you have seen. You will get this kind of polarization here. Now this more this more voltage, what will happen if we increase the voltage more and more? It is already depleted. This region is already depleted with holes. You will have only ions here. This region is already depleted. Holes have gone back to the bulk. This region is already depleted with holes. Now in p-type semiconductor, we know we have this minority electrons are minority there in p-type semiconductor, and this minority electrons now attracted by this positive voltage and come towards the interface. These are the minority electrons. Now what happened? This minority electrons come back, and now again the capacitance became this much only. So after this minimum point, what is this minimum point? This is C0 parallel with CD. This minimum capacitance is C0 parallel with CD. And again, if you increase more positive voltage, what will happen? This will again rise back. This will again rise back and stay constant at this C0 voltage. So this region is called inversion region. So again the capacitance is C0 only. Now the parallel component will go away. So if you see from this graph, this region we call it as accumulation region, and this region we call it as depletion region, and this entire region is inversion. And if you want to break this region into two regions, we call it as weak inversion, and this we call it as strong inversion. We call the MOS structure or MOSCAP or MOSFET MOS structure to be strongly inverted if the number of inversion charges like here it's electrons becomes equal to the original charges in the bulk. This bulk has holes. So what I mean by this line is, if the density of electrons in the inversion layer is equal to the holes in the bulk, density here, density of electrons in the inversion layer is equal to density of holes in the bulk. If I use n-type semiconductor, it is opposite in the bulk semiconductor. So here it is. This CV characteristics is very important. You will characterize the lot of things from this CV characteristics. Like for example, we can calculate the thickness of oxide layer, we can calculate the maximum depletion layer width, and all from this CV characteristics, and that is out of scope for this video. And if I draw the CV characteristics now for P-type semiconductor, it's look like this, C and V. And for n-type semiconductor, suppose this is for p-type semiconductor, and for n-type semiconductor, this looks like it starts here and come here. This is the C, and this is the C, and this is the V. Now this is happening when we are applying a DC voltage. Suppose if I apply AC voltage, we can say DC or a low frequency voltage. Low frequency characteristics, we call it as low frequency characteristics, CV characteristics of a MOSFET. C voltage or high frequency. And then what will happen? If we apply high frequency, then there won't be enough time for high frequency. There won't be enough time to form inversion layer. So high frequency CV characteristics look like that this is C, this is V, and high frequency CV characteristics look like this. This is high frequency. For more such concepts, please share this video, subscribe to the channel, and like it. Press the bell icon. We'll continue MOSFET in the next video.